Well, hello, people. Today we are talking about sig figs, units, and dimensional analysis. Here's a question for you. First, most of this should be a review for you, but a quick question for you. Wait, let's get rid of this. Boop. And I'm going to change up my pen here. Okay, if I gave you these numbers, if I gave you this set of numbers here, would you say that these are the same? Well, in your math class, maybe some of these would be the same. So maybe like this one would be the same as this one, would be the same as this one. But in science, that's not true. We use sig figs, or significant figures, to communicate the specificity or the precision of our measuring instrument. These three numbers might be the same number in math class, but in science, this one has one less decimal place, this one has one more decimal place, and this one has 1, 2, 3, 4 more decimal places. This is communicating something about the instrument that was used to measure these numbers. This one communicates that a much more precise instrument was used, and this one communicates that a much less precise instrument was used. In other words, we know this number with a higher degree of precision than we know this number. You already know quite a bit about sig figs, so I'll go through this pretty quickly here. But let me go ahead and pause and clear out my whiteboard, and then we'll talk about sig fig rules. One sec. Okay, here are the sig fig rules that you already know. If a number has a non-zero digit, you know that that means that that number is always significant. Any non-zero digit is always a significant number. We know that leading zeros are never significant. We know that trailing zeros are, well, sometimes significant. They are not significant if they are before the decimal place. And they are significant if they are after the decimal place. Sandwich zeros, we know, are always significant. Let's take a look at a few examples. We'll try some numbers like this. Okay, how many sig figs in each of these numbers? Well, for this first one, you have a 2. The 2 is always significant, so that's at least one significant figure. Then you have these trailing zeros. You have 1, 2, 3 of them. These trailing zeros are before the decimal place. Notice the decimal place is right here. So these 3 zeros are not significant. That means that this number has one significant figure. This number, 2001, it has one non-zero number, another non-zero number, so that's two significant figures, and these two zeros here are smushed between these two numbers, these two non-zero numbers, and so that means that you have 1, 2, 3, 4 significant figures since these two zeros are sandwiched. Here we have one non-zero digit, so that is significant. Over here, we have a zero that is a trailing zero that is after the decimal place, which means this trailing zero is significant. Because you have a significant figure over here and a significant figure over here, the rest of these zeros are now sandwiched between those two, and so all 1, 2, 3 of these zeros become significant. That means here we have 5 significant figures. This guy here, you have one non-zero digit, then you have 3 zeros, but those 3 zeros, they're trailing zeros, but they come before the decimal place. But here's kind of a sneaky trick that you can use with significant figures. This decimal place effectively sandwiches the zeros. And so then we would say that this number is precise all the way down to the ones place. Because it's precise down to the ones place, we have 1, 2, 3, 4 significant figures. Lastly, in this number, we have 1, 2, 3, 4 leading zeros. Leading zeros are never significant, even if they're after the decimal place. Then we have one non-zero digit, that's significant. And then finally, this last zero is a trailing zero, but it's after the decimal place. So that gives us 2 sig figs here. This should be somewhat of a review for you. I don't go too in-depth into sig figs because my assumption is that you've been doing sig figs since 8th grade and you should feel pretty good on them at this point. Sometimes we need to use scientific notation in order to write the number of sig figs correctly. For example, suppose that I wanted to write the number, let me see where I want to do this. I'm going to move myself. Move up here. Okay, suppose that I wanted to write the number 2,000 meters. And suppose that I wanted to write this number 2,000 meters with 2 significant figures. Well, you could see how this is going to be really tricky to do, because if I could put a decimal place right here, that would make it 4 significant figures, which is not what I want. I want to show it to correct to the hundredths place. In order to do that, I have to use scientific notation. The way that I do it is I move the decimal place all the way until it's right behind the very front number. So I'd move the decimal place 1, 2, 3 spots. And then I'd write times 10 to the however many places I moved the decimal. Because I moved the decimal place 1, 2, 3, I'm going to go with a 3 here. If I made a big number smaller, my exponent here is positive, because in order to undo it, I would have to make it bigger. So it's times 10 to the positive third to make it bigger. Now, in order to get this to 2 significant figures, what I'm going to want to do is I really just want 2 significant figures. These are trailing zeros here. So I can erase them like this. And now I'm left with 2 significant figures. Check it out. Now, this number is still 2,000 because 2.0 times 10 to the third is 2,000. But it only has 2 significant figures written down. Okay, next is, let's look at another one. Let's look at one that's too small, or a number that's really small. Let's say that I had a number like 0.0002 meters, and I wanted to write that with 3 significant figures. Well, I could turn this into scientific notation. If I took this little decimal place, I moved it over 1, 2, 3, 4 spots like this, and I would get 2 point. Now I only want 3 significant figures, so I'm only going to keep 3 numbers total, 2.00. Now I say times 10 to the -4th meters because I made this number. This number is a very, very small number in real life, so it has to have a negative exponent. A positive exponent corresponds to a number that's very big in not scientific notation. A negative number corresponds to a number that is very small in not scientific notation. Proper scientific notation always puts the decimal place right after the number, but you could also have cases where you have improper scientific notation in which there's still a decimal place somewhere and there's still times 10 to the something, but the decimal place is in the wrong spot. For example, you could have 20.0 times 10 to the second. This would be improper scientific notation because the decimal place isn't behind the first digit, but it still communicates that this number is actually 20, like this, 2,000, because you move the decimal place over 2. Okay, that's a little bit on significant figures. Let's talk about how to keep significant figures when you're multiplying, dividing, adding, and subtracting. I'm going to get a new page pulled up here. 1 second. Okay, let's talk about multiplying and dividing and adding and subtracting with sig figs. The whole purpose of sig figs is to communicate something about the precision of your measuring instrument. If I made a measurement and then I made another measurement, say that I measured something to be 200 and let's say 200.58 meters. And let's say that I also measured something to be 18.2 meters. These numbers right now are communicating something about the precision of my measuring instruments that I use to make each of these measurements. Well, if I multiplied these two measurements together, I would get a new number, and that new number should reflect the precision of my original measuring instruments. If you do this calculation, you'll find that when you multiply 200.58 and 18.2, you get something like 3,650.556 meters squared. This number, you'll see right now, does not reflect the precision of my measuring instruments. Right now, this number shows that I have more sig figs. In other words, it looks like my measuring instruments were more precise than they actually were. In order to preserve the original intention behind the significant figures of my original measurements in multiplication and division, the rule is you match the sig figs of your final answer to the sig figs on the number that has the least number of significant figures from your measurements. In this case, 200.58 has 5 significant figures, 18.2 has 3 significant figures, so our final answer should have 3 significant figures matching that 18.2. There are a few ways to write this. You can write this first as 3,650 meters squared. That's a number with 3 significant figures. Or you could write it as 3.65 times 10 to the third meter squared. Hey, Hamdia.
Hello.
Here is.
Oh, sorry.
Oh, no, don't be sorry. Thank you. Either one of these answers totally works. Let's talk about addition and subtraction rules. Oh, wait, sorry, quick pause. By the way, whenever we do multiplication, thanks so much, Hamdia. Whenever we do multiplication in physics, we always do it with these parentheses here. We'll never do multiplication with dots or with x's. We always use x's for scientific notation, but we never use them for multiplication. The reason why is because a dot and an x mean something totally different in physics. A dot usually means a dot product, and an x normally means a cross product. And so if you're doing plain old ordinary multiplication, we always use parentheses, not dots or x's. Okay, moving on. Let's talk adding and subtracting. When we add and subtract values, let's take the same measurements. Let's say that I measured something and it was 200.58 meters, and now I wanted to subtract this number, which is 18.2 meters. Our rules for addition and subtraction is that we always preserve the number of decimal places that is from the least number of decimal places from our measurements. So our original measurements are these two. The number with the least number of decimal places is this 18.2. So our final answer is going to have only one decimal place here. We write this like this. Our original answer would be I'm adding them so then I can do it in my head. Yes. Okay, 218.78 meters. And then if this right now has too many decimal places, to reflect the same number of decimal places as our number with the least number of decimal places, we're going to match it to this 18.2 here. So I'll leave it as 218.8 meters. And that will be our final answer. Now, all of this is probably old news to you. You probably already know all of these things. So this was just a very, very brief review of significant figures and what to do with significant figures. Next, we're going to be talking about units. And I'll go ahead and pull up a new tab. Bum, 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 bum. Oh gosh, I could have paused it and saved you time. Wow, I am so sorry. Here we go, a new tab. Yeah. It's almost here. It'll be here so soon. Yes. Okay, let's change up our color because now we're talking a new topic. Let's talk about units. All right. Significant figures tell us how precise a measurement is. Units tell us what kind of measurement it is. For example, there are 3 main types of things that we will measure in physics. Actually, everything else that we measure is like weirdly a combination of these things. But the 3 things that we measure in physics are mass, length, and time. If you measure a time, we use units of seconds. If you measure a length, we use units of meters. If you measure a mass, in chemistry, you learned that we use units of grams, but in physics, we use units of kilograms. Because in chemistry, we study the small stuff, and so we use grams for small stuff, but in in physics, we're talking about things like elephants, and so we use much bigger units, and so we use kilograms. These units are all what we call SI base units, or metric base units. This is opposed to the imperial system, which we use in America, where we would say that time, well, we would still say time is measured in seconds, but length we measure in inches or feet or yards or miles or that kind of thing. And then mass, actually the imperial unit of mass is called a slug, but no one ever uses it. So in science class, we use SI or metric units instead of the imperial units. We also have symbols that represent time, length, and mass. The symbol that we use to represent time is generally T. A lot of times you'll see a little delta in front of it. That is to represent a change in time. The letter that we use to represent length, sometimes we'll use L, sometimes we'll use X if it's a length in the X direction, sometimes we'll use Y if it's a length in the Y direction. For today, I'm going to call it an X. And sometimes you'll see it as a delta X because it's a change in position. Way more to come on that later this unit. And then finally, mass we represent with the letter M. Now these are our base units. If you want to make these bigger or smaller, well, in imperial units, it's very, very hard to make them bigger or smaller. For example, if we were talking in units of length, in imperial units we have inches and feet and yards and miles. And you know that if you want to convert from inches to feet, well, you got 12 inches in a foot. If you want to convert from feet to yards, well, you got 3 feet in a yard. And if you want to go from yards to miles, well, let's just skip because no one ever does that. Instead, we always go from feet to miles. We know the number, but only because we live in Denver, is 5280. I promise you, if you lived in any other state, you would never know that 5,280 feet are in a mile. Like, maybe you'd know it sometimes, but like that's not something that would be memorable to you. So this is a very, very yucky system. The metric system makes it so much easier if you want to do conversions. If you take a look at your textbook, page 12, table 3, you will see that there is a table of metric prefixes. Here's the idea. The idea is if you want to make meters bigger than meters, then let's multiply them by a multiple of 10. And if you want to make meters smaller than meters, let's divide meters by something that is a multiple of 10. And same thing with kilograms and same thing with seconds. It makes it a very universal system that's very, very easy to use. I'm going to go ahead and write out all of the prefixes that you need to know and that you need to have memorized. I'll write them all out for you here. I'm actually going to pause the video and write them out so that it kind of saves you some time. You do need to write these down in your notes because you do have to have all of these memorized by tomorrow. So let me go ahead and write them out for you really quick. Okay, here are the SI prefixes that you need to have memorized. Here we have the name of the prefix. We got pico, nano, micro, milli, centi, kilo, mega, giga, and tera. My handwriting is not the most supreme here. But you can also find them on page 12 of your textbook in table 3. Here we have the times 10 to the, so pico is times 10 to the negative 12th, nanos times 10 to the negative 9th, micros times 10 to the negative 6th, millis times 10 to the negative 3rd, so on and so forth. You can read the rest. And then we have their symbols. We got a lowercase p for pico, a lowercase n for nano. For micro, we have the Greek letter mu, milli lowercase m, centi lowercase c, kilo is a lowercase k, and then we got a capital M, capital G, capital T for mega, giga, tera. You'll notice that once we get really big, then we start using capital letters for the things that are making it really big. So that is kind of super fun. And that is pretty much all about your prefixes. You do need to have these memorized starting like yesterday, and you also need to be able to use them in unit conversions. Okay, that is a little bit on units. Let's actually do a practice unit conversion really quick. Just to make sure that you feel confident on these. Again, my guess would be that you probably already know how to do unit conversions, but this is just a little practice so that you remember all the things that you forgot over the summer about how to do unit conversions. Okay, let's take a quick look here. 1 second. Okay, let's do a quick unit conversion. Except that it's going to take about 5 years to write the words unit conversion. Okay, here we go. Let's say that you wanted to know how many micrometers are in a marathon. Well, first, you would have to know that a marathon is 26.2 miles. If we want to go from miles to micrometers, well, we got our work cut out for us. We're going to start by writing 26.2 miles because that's where we're starting, and our eventual goal is to get to micrometers. Now we're going to do little conversions all the way along the way to help us make it to micrometers. And let's start here. First, I'm going to get miles into feet. To do this, I put what I'm trying to get rid of on the bottom because I'm trying to cancel out with the miles. And I'm going with what I'm trying to get to on the top. That's feet. The next question that I ask myself is I ask how many little feet fit in one big mile. And I know that there are 5,280 feet in a mile. Now, feet is not yet micrometers, so I'm going to need another fraction. This time, I'm going to go from feet to inches. My feet will cancel out. That will look very beautiful. And so the next question that I ask myself is how many little inches are in one big foot? And I say one big foot has 12 little inches. Now I've gotten rid of my miles and I converted it to feet. I got rid of my feet and I converted it to inches, but we're not yet done. Let's go from inches into the metric system. We're going to go from inches to centimeters. Now, I know, and you should have this memorized, that 1 inch has 2.54 centimeters in it. Then we'll go from centimeters back to meters. To go from centimeters to meters, I know that there are 100 centimeters in 1 meter. And finally, we got to get into micrometers. So to go from meters to micrometers, I got to remember my prefixes. I know that micro means times 10 to the negative 6th. There are a few different ways to do this. Either I could say 1 micrometer is equal to 1 times 10 to the negative 6th meters like this, and that's one way to do it. Or I could say, hey, micrometers are tiny, and there are a lot of micrometers in a meter. So one other way that I could do this is I could say there are 1 times 10 to the 6th micrometers in a meter. Either one of those is great. Then type this into your calculator, and you multiply everything on the top, divide everything on the bottom. Notice that everything is going to cancel out. My miles will cancel out with miles. My feet will cancel out with feet. The inches cancel out with inches. The centimeters cancel out with centimeters. The meters cancel out with meters. And all of a sudden I'm left with micrometers. And all that is left is 4.22 times 10 to the 10th micrometers. And that, let me tell you, ladies and gentlemen, is a whole lot of micrometers. And there you go. There's a little practice with unit conversions. Our last topic of the day, we've talked about significant figures, we've talked about units, now we've talked about unit conversions. The last thing that we're going to talk about today is going to be dimensional analysis. Now, the rest of this stuff that we've talked about today has honestly been pretty reviewy. Like, you already probably knew everything about sig figs. We haven't probably done anything new with sig figs that you didn't already know. You already knew everything about these types of units. Even like the base SI units and that kind of thing, you knew how to do unit conversions. The one thing that you probably haven't done before in a previous class is you probably haven't done anything with dimensional analysis. But we're going to do it together now. Let's talk about dimensional analysis. Here's what dimensional analysis is. Dimensional analysis is a way to check if a physics equation is viable. In other words, could this physics equation be a real physics equation in real life? Let's say that you thought you knew an equation. Let's say that you thought you knew the equation delta x is equal to v naught delta t plus 1/2 a delta t squared. Let's say you're thinking to yourself, I'm pretty sure that's a viable, true, real-life equation. But you're sitting there at your physics test and you're like, I don't really know, man. Is that right? I'm not sure if it's right. I think it's right, but do I know that it's right? I don't know. So here's what you do. You use a little dimensional analysis to figure out if this equation is the right equation. Dimensional analysis is a way to use units to figure out if an equation is viable. Let me show you how you do it. There are 4 steps to dimensional analysis. The first step is to write the equation that you are trying to test. In this case, we got delta x is equal to v naught delta t plus 1/2 a delta t squared. The second step is to replace all of the variables with units. The same way that you would plug in numbers into an algebraic formula, instead we're going to plug in here units. Now, here's what you already know. You already know that the units of delta x are meters. You also know that the units of delta t, that's time, are seconds. And over here, we also have another delta t, which is also seconds. But let's fill in some gaps here. First, we haven't talked yet about v naught. V naught represents initial velocity, and the units of velocity are meters per second. So in the equation over here, we can write this is going to be meters per second from our v naught times seconds from our time. Then, here's a very common mistake. A lot of students then want to write 1/2 here, but what are the units of 1/2? There are no units. And so we actually write nothing for 1/2, and we don't even write the 1/2 at all. Instead, we just write the units of acceleration. A stands for acceleration. Now, we haven't talked about it yet, but we will soon. But for today, all you have to know is that the units of acceleration are meters per second squared. So I'm going to write in here, meters per second squared. Now, one other thing to notice. Here, I have delta t, so I wrote seconds, but notice that my delta t is squared. So I need to have seconds squared. And that is step 2. Step 3 is then to simplify everything the same way that you would if it were an algebraic expression. So, here's what we've got. I have meters is equal to meters divided by seconds times seconds plus meters divided by seconds squared times seconds squared. Well, check it out. Aren't seconds going to cancel out with seconds? You got seconds in the numerator and seconds in the denominator. And aren't seconds squared going to cancel out with seconds squared? So I'm going to be left with meters equals meters plus meters. Here's the idea of dimensional analysis. The idea of dimensional analysis is that if this equation is true, if it's really true that delta x is equal to v naught delta t plus 1/2 a delta t squared, then whatever the units are on this side, they have to match the units on this side. I can't say that 14 bugs is equal to 3 oranges, or even that 14 bugs is equal to 14 oranges, because 14 bugs and 14 oranges are not the same thing. But if I saw that there was bugs on this side of the equation and bugs on this side of the equation, I would say, okay, maybe that's a realistic, actually real-life viable equation. Like maybe that equation could be true. So what we see here is we're checking the units on both sides with the eventual goal of seeing, are these units the same on both sides? And what you see here is we end up with meters on this side and meters on this side. Now some students will get confused here because they'll say, well, but Miss Wilson, you have meters on this side and you have 2 meters on this side. But remember, we aren't adding together variables, we're actually combining units. If you had something that was 3 meters and something that was 3 meters, well then you would still end up with meters over here. So here's the main gist of the story, is that you have meters on this side over here, you have meters and meters on this side over here, and so step 4 is to state whether or not the equation is viable. And for this equation, because we have meters on both sides, I'm going to say, yes, this equation is viable. Now, if I ended up with meters on one side and meters times seconds on the other side, I would say, no, that's not possible, and this is not a viable equation. But in this case, I get that it is a viable equation. And that's how we do dimensional analysis, is we follow those 4 steps. And that, ladies and gentlemen, is pretty much everything from today. We started by talking about significant figures. We talked about kind of how you find out how many significant figures are in a number. We talked about how to do significant figures with addition and subtraction and multiplication and division. Oh, we also talked about scientific notation too. Then after that we talked about units. We talked about the purpose of units and the 3 base units. We talked about unit conversions. And then finally we ended class today talking about dimensional analysis. And that is pretty much the whole thing. So yeah, well, I hope that was fun for you, and I hope that you have a wonderful, wonderful rest of your day. I'll see you next time, virtually or in person. Have a great rest of your day. Bye.